Alright class, hello. Today we're going to be talking about section 3.10, which is on related rates. Now, this can be sort of a tough subject if you don't pay close attention to what you're doing. But at the same time, it really is just an application of implicit differentiation. Okay, so this is an application of implicit differentiation. To physics. Okay, and the idea basically boils down from the fact that if you have two quantities that are related to one another, then their rates of change should also be related. Right? So, for example, or let me just write that, but so if two quantities are related, then their rates of change should also be related. Right? And that's where the word comes from, or the term related rates comes from. It's just we have two or more quantities that are all related to one another in certain ways. Then if one changes, the other should also change, and they should change in a way that's related in a similar aspect. For example, when you're driving and you accelerate, okay, you can actually see related rates in action, because when you accelerate, well, your miles per hour, right, on the speedometer, that goes up. But what else goes up? Well, your RPMs also go up. Okay, if you really gun it, you'll see both those go up. So one, your acceleration is affecting the other, your RPMs, right? That's one example, a car example that you might see every day and just might not have thought about it. But you have a lot of systems within a car that are all related, and as one system changes, other systems change as well, right? You can even think of the height of the gas pedal. And as the height of the gas pedal decreases at a certain rate, you know, the, say, acceleration of the car increases. Okay, so you have many, many interrelated things. Now, for this section, we're just going to be starting on some really basic related rates ideas. This stuff will be continued on when you take your calc-based physics classes. A lot of physics problems deal with this sort of idea that, you know, once you have a lot of related quantities, the rates are going to all be related. Okay, so an example I like to start with is just a circle. Okay, so let's look at that. Okay, so we have a circle here. Consider this circle with radius r. The quantities that we can talk about with a circle, of course, are the radius, r, and two other important things will be the circumference, which we call c, and the area, which we call a. And, you know, you could say diameter, but that's just basically double the radius, so we won't worry about that. But all these quantities are basically related to one another in certain ways. So area is, or let's start with circumference. Circumference, okay, is related to the radius in the following way. Hopefully we know that. Let me shift the camera over just a tad. I've just screwed it all up. Okay, circumference is related to the radius in the following way. C is equal to 2 pi r. Hopefully you know that. All right, and area is related to r, or related to the radius, as area is pi r squared. Okay? So, now what I want to talk about here is we have a circle, and let's say that the radius starts increasing. Okay? Say it starts at some value and starts to increase. And when the radius increases, right, the whole circle starts expanding, provided it stays a circle. Okay? What must also happen to the circumference in the area when the radius starts increasing? Think about that for a second. What must those two quantities also do? Okay? They must also increase. So, okay, as the radius of this circle increases, okay, so must the circumference and the area, right? Provided it stays a circle. Now, if it doesn't stay a circle, that's a different problem, but we're not going to worry about that just yet. But yeah, as the radius increases by a certain amount, the area certainly does too, and the circumference has to as well. Okay, so basically, what related rates allow us to do, well, here we have, so what I'll say is, in other words, the rates of C and A are also related to the rate of R. And essentially what that means is that the derivative with respect to t of the circumference is related to the rate of r, which is dr dt, right? The derivative of the radius with respect to t. And the derivative of the radius with respect to t is related to the derivative of the area with respect to t. Right? They're all related to one another. Okay, and this is what we're using because what we're going to do, right, is let me explain this a little better, why we're using d of t and all that. If the radius begins to increase, over time, right, then we can think of it, or we can consider r as a function of t, right? Something like r of t, right? Because at each time we'll have a different radius. It's increasing over time, so we'll get bigger and bigger radii, but at each t we can take a look at it, meaning that the radius is a function of t. And we also have that the circumference also changes, or also increases over time. Meaning it is also a function of t, and meaning we can take both sides of that equation we have with respect to t. We can take the derivative. So meaning we can differentiate both sides, or both functions, or both quantities with respect to t, or time. Okay? In other words, we can do this to both quantities. Alright, so we know that circumference is related to radius in the following way, that c is equal to 2 pi r. Now how we get the rates related, okay, and so they're related, so we know the rates are related. I mean, that's the first step, obviously. As the radius increases, the circumference also increases. But how do we find how those rates are related? Well, how do we find the relation between dc over dt and dr over dt? Well, the answer is implicit differentiation. Okay? The only difference here, we don't have y's. Okay? We'll be taking derivatives with respect to t. And anytime we don't see a t, we're going to throw a d whatever is over dt. Okay? So this is in terms of d over dt. Okay? So that means we differentiate both sides of this expression with respect to t. So we have d over dt of c is equal to d over dt of 2 pi r. Okay? Now, taking the derivative, well, the derivative of c is 1, but we also have to use implicit differentiation, so this will be dc dt. And that 2 pi constant, we can just move outside, and the derivative of r with respect to t is simply dr dt. So this is how the rates are actually related. The rate of the circumference is 2 pi times the rate of the radius. Okay, so using implicit differentiation, we found that the rate of c is 2 pi times the rate of r. Okay. So what this basically means is that if r is increasing at, I don't know, 6 feet per second, then c is increasing at 2 pi times 6, so at 12 pi feet per second. Right, and how you get that is if we have dc over dt is 2 pi times dr over dt, we just put in the value for dr dt, which I just said is 6 feet per second, and we multiply to get the 12 pi feet per second. And dc over dt is, of course, the rate. Okay? All right, and that is basically how we get these things related. Now, it kind of makes sense, I think, because if you think about what the circumference is always just 2 pi times the radius. So if the radius increases by 6 feet, then the circumference will increase by 2 pi times that 6 feet. So it makes sense that their rates are related in this sense. Let's look at the area next, because that one is actually a little more interesting, right? Because we have the area, right, is pi r squared, and we want to see how these rates are related. Okay, so how are these rates related? And again, we take the derivative with respect to t of both sides using implicit differentiation. So the derivative of a with respect to t will be equal to the derivative with respect to t of pi r squared. Okay, now the derivative of a is simply dA dt, right? That's about all you can do with that. But the pi, comes outside. And the derivative of r squared, well, what is the derivative of r squared using implicit differentiation? Well, r squared is going to be 2r then times dr over dt. Okay. So what we basically have is that the rate of change of the area is equal to 2 pi r times the rate of the radius. Okay, so this brings us to what related rates, the complication of the related rates, where we really start to get down into what makes these tick, is that I have an r sitting here, and you'll notice that this is actually the circumference, right? So the rate of change of the area is actually the circumference times the rate of change of the radius. Now, since we have this radius in here, we'll note that even if the radius increases at a constant rate, say it always increases at 2 feet per second, the rate of the area is not going to be constant, because we'll have this thing increasing as well. It will get bigger and bigger over time. And that makes sense, actually, because when you think of if the radius only increases by 1, well, the area increases by a whole lot more. Okay, a whole lot more. Whereas the circumference just kind of increases by about a similar amount. Okay, and this also brings into the fact that related rates look at the rates at a particular moment. Okay, so related rates look at a situation, or at a system, I'll say, at an instant, at a particular instant. And it can be many instances, but there's that word instantaneous. We can only basically take a freeze frame of what's going on and take a look at what is going on at that particular second. Well, we don't know necessarily what's going on all the time, always. All right, so for example, we need more information, because if I say that if the radius is increasing at, let's say, 2 feet per second, or 2 feet per second is fine, then what we have is that the rate of the area is going to be 2 pi r dr dt, which is 2 pi r times 2 feet per second, but we still don't have all the information, right? Because what this says is that the radius, or the area, now is always increasing at 2 pi r feet per second, which means we need more information. So at the moment, the radius reaches 1 foot, okay, then the rate of change of the area will be 4 pi times r, which is 1 foot, feet per second. And there we go. We'll end up with 4 pi feet squared per second, right? And since this is area, it should be increasing and decreasing in feet squared or square feet per second. Okay, but right, this isn't how fast the area is always increasing. Okay, when the radius reaches, let's say 10 feet, okay, the rate of the area, dA by dt, if you remember, actually I have it right here, oops, which we found was 4 pi r feet per second, is going to be 4 pi r feet per second. So r here is 10 feet. Okay, so we'll end up with 40 pi feet squared per second. So even though in this particular problem I have that the radius is increasing at, and I'll just say at a constant, right, it's a constant 2 feet per second. This won't always happen, but just because the radius is increasing at a constant 2 feet per second, the area is not. The area, when the radius hits 1 foot, is increasing at 4 pi feet squared per second. But when the radius hits 10 feet, the rate of the area has increased or accelerated up to 40 pi square feet per second. Okay, so related rates can only analyze things at particular moments. Okay, so we can only analyze instants. Okay, and that's it. And at each particular instant, you're going to get different rates, even if one of those rates is constant. And often it won't be. Often you'll have to be told, okay, at this instant, the rate is this, and the length is that. Okay? Okay. So now we're going to look at examples of actually solving related rates problems, more than just, hey, I have a circle that's increasing. Okay? Show you like the applicable things of this stuff. Okay, so when solving related rates problems, there's a process you need to go through, and you've got to be very careful about what you're doing. So the first thing you're going to do, I typically, I decide what things are, going to be constant, which things are going to be variables. I label my variables, I fill in my constants. I also like to draw a picture if necessary, but we're going to set up the problem. And fill in any constants, because in a lot of these problems you will have constant values that aren't ever going to change, and you fill those in, and what's nice about those is, well, the derivative of a constant is 0, so they'll disappear, or they'll just be a nice little thing that sits outside. Okay, now so we're going to set up the problem, fill in any constants, and label your variables. Okay, so here's how you identify these. Constants don't change. Variables vary over time. Okay, so if you look at a quantity and you think, okay, is this thing changing over time? Then it's going to get a variable name like x or y or w. Is it staying fixed? Right? Is it staying fixed? If so, that's a constant. You're going to fill in that number. And these are the only numbers you fill in on this step. Okay? So only plug in constants. Here. Okay, in this first step. If you plug in everything, because you're going to be given a lot of information. If you plug in everything, you're going to mess the whole problem up. Okay, because you're not going to, when you take the derivative, you're going to have just a bunch of constants. Nothing's going to work right. Only plug in constants. If you're told information about a variable, don't worry about it yet. Okay, step 2 then. Okay, and is get or find a formula that relates the important quantities. Right. So there might be some quantities that you don't really need to worry about. For example, if you're looking at area, you know, you probably don't need to start worrying about circumference if you're only looking at area and you just need radius and area. But basically you want to find the formula that relates all the important quantities. And once you do that, then step 3 is you're going to use implicit differentiation. Right? So 3, use implicit differentiation. In other words, take the derivative with respect to t of both sides. Okay? And from here, 4, you should be able to identify the needed rate, because that's usually what you're looking for. Needed rate. And you can solve for it. Right? Or, you know, you can plug in values at this point. Okay, so then finally, the last step, and this is important. Now you plug in everything to finish the problem. All right? So, let's look at an example, and we'll go through these steps and see how it goes. Okay? Okay, so here's our question. We have a 5-foot ladder is leaning against a wall, and it begins to slide down the wall. So this is like the typical calculus problem, related rates problem, right? You probably see this in every calculus class that's ever been. But we have a 5-foot ladder, it's leaning against the wall, and the top of the ladder begins to slide down the wall, which means at the same time, provided that you know it's sliding straight down, okay? It's not, you know, falling to the left or right or anything like that. It's falling straight down. As that happens, right, the base of the ladder starts to slide away from the wall. So for example, if I was going to draw a picture, here's my ladder leaning against the wall, and the top of the ladder begins to slide down, and as that happens, right, what happens to the base? Well, it has to slide back, right, and eventually it will hit the ground. Okay? So what we're told is that, so here's the basic situation. All right? Now, when the top of the ladder is 4 feet above the ground, the top is falling at 0.5 feet per second. So what we have here is that we're only looking at this moment, right, when the ladder is 4 feet above the ground, and at that moment we are told that the ladder is falling at 0.5 feet per second. Okay. Now, at what rate is the base of the ladder sliding away from the wall? So we have that this is what we're looking for, right? This rate. Okay, so here's all the information I'm given. I'm going to put a little bit more in my picture. All right, so first of all, let's talk about my variables. Now, the height of the ladder above the ground, I'm going to call x because it's varying over time, right? It's falling. Since it's varying, I'm giving it a variable. And this guy here, this length, which is the length that the say base of the ladder, its distance from the wall, it's also changing over time because as x decreases, y will actually be increasing. So since it's a variable, I'm going to call it y. And then the length of the ladder is not changing. Right? So the length of the ladder is fixed. It's not changing. So I'm going to just call it 5 feet. Okay. Now, this is the only thing I'm allowed to plug in right now. All this other information I'm going to save until later. In fact, I'm going to erase it because I don't need it yet. All I need is the fact that my x value is decreasing, my y value is increasing, and this length stays constant. Now, we need a formula that relates x and y. Okay, and we have a right triangle here. Probably the quickest one you could think of would be the Pythagorean theorem. In fact, that's what we're going to go with. All right, so by the Pythagorean theorem, let me keep my picture up here. Okay, so the Pythagorean theorem gives me that x squared plus y squared is equal to 5 squared. Okay, so there's my formula, and notice the only number I put in was the hypotenuse, which is fixed, right? So we got a fixed 5 put in. All right, the x and y, they are varying over time, so they stay as variables. They don't get plugged in until later. Now, the next step, I've set up my problem, I've gotten a formula that relates. Now we're going to take the derivative of both sides. Okay, so I'll get the derivative, and actually let me just start this over here. X squared plus y squared is equal to 25. So I'm going to take the derivative of both guys. And this on the other side. Okay, so the derivative with respect to t of x squared is going to be 2x, and since we're using implicit differentiation, this will be 2 or dx over dt. Okay, then the derivative of y squared, since we're using implicit differentiation, will be 2y dy dt. This one should probably look a little more familiar. Okay, this one maybe not, but since we're taking the derivative of t, or with respect to t, anytime we don't see t, we have to throw in the derivative of that thing. Okay, and then over here, the derivative of a constant is 0. Okay, now we've done this, and now we need to look at solving for the one that we want. Now let's go back to our problem here. Right, so we're asked, at what rate is the base of the ladder sliding away from the wall? Now, what rate would that be? Would that be the rate of x, or is that the rate of y? Well, That's what we're looking for, is the rate of y. Right? We're actually given the rate of x. What is the rate of x? Go ahead and say it. Look like an idiot while you're listening to this. Okay. It's given to us as the 0.5 feet per second. So what we're actually looking to solve for is we're going to solve for dy over dt. Now, you don't have to solve like this. You can plug everything in now if you want and solve, but personally I like to solve, then plug everything in. That's just the way my mind works, because to me, sometimes these numbers get really messy when you plug them in, so I rather have it all on one side and simplify down, but it doesn't matter as long as you get the right answer out. But we're solving for this guy. So this term is going to move over to the other side, and I'll get 2y times dy over dt is equal to negative 2x dx over dt. And then I'm going to divide both sides by 2y to give me that dy over dt is equal to negative x over y times dx over dt. Noting that the 2's cancel when I do that. And now we can plug everything in. Okay, so now we plug everything in. And this is the only time we're allowed to do this, at the very end. Okay, don't plug these values in at the beginning, you have to do it at the end. So what am I going to plug in? Well, do I have x? I go back to my information. We're told that this is when the top of the ladder is 4 feet above the ground. So we are given this length at this moment is 4 feet. Okay, so x is 4 feet. So let me put that in for x. Okay, so I'll get negative x, we'll have 4 feet all over. Now y, do we have y? Well, we are not told y, but we can actually find the missing piece using the Pythagorean theorem. Okay, and this is one of our special triangles. If this is 4 feet and this is 5 feet, what must this be? 3 feet. Okay, so the moment when the top of the ladder is 4 feet above the ground, the distance from the wall to the base of the ladder must be 3 feet. So I'm going to go ahead and put that in for y. So y is 3 feet. And the rate of change, dx dt, we are actually given that. Dx over dt, we're told, is 0.5 feet per second. Now we have to be careful here. Because the ladder is falling, what does that mean? It means that the rate that we're given when we put it in as a velocity is going to be negative 0.5 feet per second, since it's falling. Right? You've got to be very careful about that. So this is going to be, when I put this in, negative 0.5 feet per second. So the feet here actually cancel. Okay, and this is 0.5, so that's 1/2, so that's actually going to cancel with the 4, and it's going to give me that dy over dt, its rate, and I have a negative and a negative, so I'm going to get a positive. I'm going to have 2/3 feet per second when I'm finished. All right, and 2/3, that's about 0.666, or 0.6 repeating. Okay, so you know that 2/3 feet per second, if that doesn't really mean much to you, you could say that that's about 0.6 repeating feet per second. And a lot of these applications, the decimal is going to help out a little bit. And there we go. Okay, that's our first related rates problem taken care of. Remember, you set up the problem, you plug in your constants but nothing else, get a formula that relates everything, take the derivative of both sides using implicit differentiation. Then after you take the derivative, then you can plug things in, or you can solve and plug things in, however you like to do it. After this point, you've just got to be very careful about plugging in negatives and whatnot. Alright, next example, let's move this into 3 dimensions here. Let's say I have a spherical balloon is being deflated, okay, at a constant rate of 3 cubic centimeters per minute. Okay. Now, at what rate is the radius changing when the radius is 6 centimeters? So, I always like to draw a picture, but it's not always necessary. But I have a spherical balloon here, okay, and it's deflating. So that means the volume is decreasing, right, over time. So what do you think is happening to the radius? That's what we're asking about. What's the radius, or what rate is the radius changing at? That should be a question. Okay, and it should be decreasing, right? The radius should be decreasing. Okay, so here's what we're going to do. We have the volume is, and that I'll put in here. The volume is decreasing over time, so the radius should be decreasing over time. So we need a formula okay, that relates these two. Relates V and R, and of course that's just going to be the formula for the volume of a sphere, which is 4/3 pi r cubed. Okay. Right? There are no constants to speak of here. Okay, so there are no constants, right? Because the radius is varying, the volume is varying. Those are the only 2 things we're looking at. So everything is changing. There's no constant here. So there's no constant to fill in. So we're just going to take the derivative. Okay, we're just going to use implicit differentiation. So we'll have derivative of V is going to be equal to the derivative of 4/3 pi r cubed. Okay, now I get that the derivative of V on this side. About the only way we can really write that is going to be dV over dt. Okay, and now this will be, the constant will come outside, 4/3 pi, and the derivative of r cubed is what? It's going to be 3r squared, and what do we have to throw in here? Let's write a dr over dt. Okay. Now, this is nice, the 3's cancel, and so we get on this side of 4 pi r squared dr dt. Now, check this out. I have not even, okay, started. First of all, I've gone this far, and I have not even thought about what I'm looking for. I mentioned it, but I didn't need to know it. I just kind of did this mechanically, right? It's because I wanted to see how the rate of the volume was related to the rate of the radius, and I've found that the rate of the volume is going to be 4 pi r squared times the rate of the radius. Now that I have this information, I can actually worry about solving the problem, and now it's a matter of plugging things into the right spot and solving. Now, of course, I could go ahead and move things over or do whatever first and then plug in. That's what I usually like to do. But let's see here. What am I told? Okay, I'm told that the spherical balloon is being deflated at a constant rate of 3 cubic centimeters. So I'm given dV dt, right? That's the volume. You know that because that's cubic centimeters. What rate is the radius changing when the radius is 6 centimeters? Okay, so at what rate is the radius changing? That's a key word to let me know that I'm looking for dr dt. So this is what I'm looking for. Okay, so what I'm going to do is move the other crap over to the other side so that what I'm basically dealing with On this side I have 1 over 4 pi r squared times dv dt is equal to dr over dt. So, right? So this is what I'm looking for. And this is all stuff I know, and so I can just plug and chug, right? Okay. So, let's get to it. So I know that the spherical balloon is being deflated at a constant rate of 3 cubic centimeters. You don't see that. Let me bring that back up. Constant rate of 3 cubic centimeters. Now, if it's being deflated, that means I need to put in a negative 3 cubic centimeters per minute. Okay, then I'll have 1 over 4 pi, and this will be the radius. We're told we're looking at the system, we freeze frame it at 6 centimeters. Right, so imagine it's all deflating, and here, you know, we have a sphere and it gets smaller and smaller, and we freeze the frame at 6 centimeters and take a look at what's going on. So at this moment that we're looking at, we have 6 centimeters. And check this out, I didn't even put that in until I was already at the almost the end of the problem. Right, so this will be 6 centimeters squared. Okay. Okay, any questions there? Well, sorry, force of habit. So, and this whole thing is equal to dr over dt. Okay. So what happens is I get 1 over 4 pi times 36 centimeters squared times negative 3 centimeters cubed per minute. Okay, so the centimeters squared will cancel with the centimeters cubed and just leave centimeters. This is important because what rate should the radius be in? It should be in centimeters per minute. Okay, so we got that. And that 3 cancels with the 36 and leaves a 12. So I have a 12 down here, which will then multiply by that 4 to give me 1 over 48 pi centimeters per minute. Okay, now that is not really the greatest rate in the world if I tell you that, oh hey, at this moment the radius is, oh, and I lost my negative, sorry. If I say it's, you know, changing into negative 1 over 48 pi centimeters per minute, you might think I'm crazy, right? So, let's go ahead and see what that is. 1 over 48 pi ends up being about 0.0066. So I'm going to round it to about that. I'm asked often, what should I round to if you're not told significant digits or you don't have enough information for that. I usually just round to what's interesting. You know, you get to a certain point where it's not that interesting, but here's about 2 significant digits, so that seems good to me. Okay, so there we go, and a good way to check if you're right or not, I got a negative value. That actually makes sense, because if the right, the volume's decreasing at 3 cubic centimeters per minute, but that's, I mean, the radius should be decreasing at a much slower rate, okay, because the volume increases and decreases much faster just because there's so much more of it. Okay, so remember, when you set up your problem, you only plug in constants to begin with, and only plug in the rest once you're finished. Okay, here's another 3D example, and one I quite like. Let's say I have a metal cylinder or a can or something that's being crushed over time. Okay, and let's just say the volume of the cylinder is 36 pi centimeters cubed. Okay? Now, what we're asked is when the height reaches 1 centimeter, it is decreasing at a rate of 1/9 centimeters per minute. So That wording is a little ambiguous, but basically we're just talking about the height there. So the rate of the height at that minute is 1/9 centimeters per minute, and the height has reached 1 centimeter. Okay, now we're asked what rate is the radius changing at this moment. So here's basically what's going on. I have this cylinder, let's say it looks like this. Okay. So we've got the height, and we've got the radius, and it's being crushed over time. So eventually it's going to look more like this. Okay, so here's the radius, and here's the height. Okay, so the can's being crushed and in such a way that the height is decreasing and the radius is increasing, right? Because we're crushing the can, but the volume should stay constant. The volume should stay the same, okay? And so now what we want is a formula that relates these two, and of course the volume of a cylinder, that's actually an easy one that you should know, is pi r squared h, right? It's just the area of the circle times the height. That's where a lot of formulas for volumes come from. Now, I can actually fill in some constants because the radius is changing over time, the height is changing over time, but what isn't changing over time? And that answer is, of course, the volume. So I'm going to go ahead and fill in the volume. The volume is 36 pi, which will be equal to pi r squared h. And actually, I can simplify this problem a little bit. I have pi on both sides, so let's go ahead and divide those out to get that 36 is equal to pi r squared. Oops, sorry, messed that up. Is equal to r squared h. That's just going to simplify things a little bit, get rid of those constants out front. We don't have to mess with pi. Okay. Now we've got our formula that relates the variables and with the constant put in. Remember, the only thing I put in there was a constant at this point. Now we'll take the derivative of both sides. Get the derivative of 36 is equal to the derivative with respect to t of r squared h. Okay. So let's keep the pictures up there because I like them. Now, what's the derivative of 36? That's going to be 0. Then the derivative of r squared h. Well, here, what makes this problem interesting, an interesting example, is we actually have to use the product rule here. The product rule, it's going to be the derivative of the first, which will be 2r times dr dt. Okay, so there's the derivative of the first guy times the second guy left alone plus the first guy left alone times the derivative of the second, which is just h, so that will be dh dt. Okay. So let me rewrite this so it looks a little better. I have now 0 is equal to 2rh dr dt plus r squared dh dt. Okay. Now I can concern myself with what we're looking for. Okay, let's see here. We're asked, at what rate is the radius changing at this moment? What this is asking for is dr dt. How do I know? I see the word rate, which means derivative. And I see the word radius, which means, of course, r. That's what I'm looking for. So what we're looking for is this. Okay. So using the same idea with implicit differentiation, I'm going to move this guy over to this side, and so I'll get negative r squared dh dt is equal to 2rh dr dt, and then finally I'll divide that over. So I have negative r squared dh dt over 2rh, and I have these r's cancel. Okay, so finally I have that dr dt is equal to negative r times dh dt all over 2 times h. Okay. Now I can fill things in. Now, of course, you can fill things in up here if you want and then solve, but I prefer to do it this way, but you can do it that way as well. Now, let's go through what we're looking for. dh dt, are we given that? And we are. We're told that the height is decreasing at a rate of 9 centimeters per minute, and what we have to be careful about is, since it's decreasing, what is dh dt? It will be negative 1/9. Okay, so what I have is dr by dt is, I'll put in the negative r in just a second, but dh dt ends up being negative 1/9 centimeters per minute. All over. Okay. Now, we have 2 times h, and h we're given at this moment, right? We're told that the height reaches 1 centimeter, so the height at this moment is 1 centimeter. So I'll go ahead and plug that in. And we have, say, some of these centimeters canceling, but I'll more about that in a second. And then finally, do I have the radius at this moment? And the problem here is I'm not actually told what the radius is. Right? It's not given to me. I've already found this. I found this. I'm not told about the radius, but I can actually find it. So if there's a piece of information you're not given, like that first example we looked at, we weren't given the length of the base, but we could find it with the Pythagorean theorem, our formula. Here we're going to need to find r using our formula, and we do that in this way. Okay, I have 36 is equal to r squared h, so 36 will be equal to r squared times 1, since h is 1 in this case, so I have r squared is equal to 36, giving me that r is equal to 6 centimeters. Okay. So I'll put that in. Okay, so these centimeters cancel. The 2 cancels with this and leaves a 3. That 3 cancels with the 9 and leaves a 3. So at the very end of the day, I get 1/3 centimeters per minute. Okay, provided I did all that right. Okay, and there we go. So at this moment, if the height is decreasing at 1/9 centimeter per minute, the radius is actually increasing out this way at 1/3 centimeters per minute. Okay, the last example I want to look at, and it's one that causes some people a lot of problems, but it's when we have related rates with angles. Okay, and what this usually entails is basically setting up a trig function. Okay, so let's say we have a lighthouse that's 6 miles south of a shore here. And I have this written over to the side, but basically, right, the light is spinning around, and so around here it's going to hit the shore and, spin around. So what we have here is 4 miles across on the shore. we have the light hits this point P. And what happens is when the beam reaches the point P, the light is traveling across the shore at 25 miles per hour. Okay, which seems legit, you know. What we want to find is at this moment, what rate is the light spinning around at, right? In RPM, rotations per minute. So how fast is that light spinning around when that happens? So this is a question of RPM spinning, very important for all you engineers out there. Okay, so here's basically what we're going to do. Now, this point P is 4 miles away from this point directly north of the lighthouse. Okay, so what we want to do is find the rate at which it's spinning, and what that basically means is as you know the light spins, we have this triangle being made. What's happening is that angle theta is increasing, right? Because as this length increases this way, the angle theta is increasing. Okay. All right. So angle theta is increasing, and this distance here is also increasing. So that I'm going to call x. That's my variable there, and theta is my other variable. This 6 miles is a constant. So I want to find a formula that relates x and theta. And how we do that is we're going to use a trig function, right? Now, there are many trig functions out there. You might think, well, can we use sine? But sine uses a hypotenuse, and we don't know the hypotenuse. We know the side opposite, which is x, and we know the side adjacent. Now, which trig function gives us the side opposite and the side adjacent? Tangent does. So we're going to have tangent of theta. That's the one we're going to use. So tangent theta is going to be equal to adjacent, which is x, over, it's going to be opposite, which is x, over adjacent, which is 6. And now that we've got this formula, now we are going to use implicit differentiation to take the derivative with respect to t of everything. Okay? So, when I go to do that, run out of room a little bit here. When I go to do that, I'm going to have the derivative with respect to t of tangent theta is equal to the derivative with respect to t of x over 6. Okay, and this is actually a pretty simple derivative. Derivative of tangent is secant squared theta times d theta dt. And here's the only difference here with related rates dealing with angles. This is where your d theta dt is coming about, and that's actually what we're looking for. So this is our rotation rates come from here. Okay, and then the derivative with respect to t of x over 6, well, that's just 1/6 times x, so that's just going to be 1/6 dx dt. Right, and we know dx dt is 25 miles per hour, so you know it's just a matter of moving this over, because this is the rate that we're looking for. So now we're going to solve for d theta dt. Now, solving for d theta dt, when I move secant over, well, 1 over secant is going to be cosine. So I'm just going to get that d theta over dt is going to be 1/6 times dx dt times cosine squared theta. Okay, now a lot of people will actually try and solve for theta in these problems, but you don't have to do that because you just get d theta dt all by itself and then a cosine, which we can actually end up finding. And I think I made a typo here. This should actually be 8 miles. Sorry about that. 8 miles there. Okay. So now we're going to start plugging in all of our values. So we'll plug in our values. We know dx dt, right, is 25 miles per hour. So let's go ahead and plug that in. 25 miles per hour. And what about cosine squared theta? Some people might think, oh crap, I've got to solve for theta, I've got to find values, but actually cosine of theta, if you remember, is just going to be the adjacent over hypotenuse. So it's just going to be 6 miles over the hypotenuse. So we just need to find the hypotenuse, and if you use the Pythagorean theorem, I'll give you a chance to do that. What do you find? You should end up getting 10 miles. Okay. So 6 over 10 miles over miles, that cancels, so I'm just going to get 3/5. Okay. So I'm squaring cosine, so I'm going to have cosine theta is 3/5, so this is 3/5 squared. Okay. And I should say this 1/6, I should have put miles here the whole way down because, well, we'll see in just a second. Don't mind all this stuff up here, that's a different problem. Okay, so I end up getting I'll do it down here, 1 over 6 miles times 25, let me say this miles per hour, right, times 9/25. So the 9 will cancel with the 9 will cancel with the 6. It will leave a 2 down here and a 3 up here. The 25s cancel, and so I end up with 3/2. These miles cancel, and we have 3/2 something per hour. And you might be wondering what's going on, where our units went, and actually angles are considered a unitless measure, right? When all your units cancel out in problems like this, what you actually end up with is radians per hour. Okay, so we have that the derivative of theta with respect to t is 3/2 radians per hour, but we weren't asked for radians per hour. We were actually asked for rotations per minute. So I can get it into minutes pretty easily. If I want minutes down here, hours up here, well, in 1 hour there's 60 minutes, so that's easy enough to get minutes in the bottom. But I want to cancel out radians and get rotations. And how does one go about doing that? Well, actually, how many radians are in a single rotation? Okay, so I want one rotation up at the top. And how many radians are in a rotation? 2 pi. Okay, so the rads cancel, and I'm left with rotations per minute, which will be RPM. So basically what I have, let's see, the 3 will cancel with the 60 and leave a 20. So I basically have 1 over 80 pi RPM. Okay, now let's find what that actually equals. I'm using our handy calculator here, and I wrote 20 and I said 40. It's 40. No, sorry, 80. God. Sorry, end of the lecture. Okay, so this is 80 pi all right, which is about the rate at which the angle is rotating at is about 0.004 RPMs, depending on how you round. Okay, and just about every way you round, you're going to get about, well, not every way, but in many ways, you're going to get about 0.004 RPMs. Okay. All right. So that is that for related rates. Again, the problem with these types of problems, so there's tons of different examples, and we already see how long this lecture has gotten. And I only did about 4 examples. There are many, many other options out there, and I can't go over every single type. All right, you're going to have to sit down and really think about some of these before you get them. Okay. So hopefully the worksheet will help, and I'll talk to you next time. Cheers.